Hello, scientists! Today we're going to do a lab on pulleys. That's lab 606, pulleys and work. The first thing you want to do is watch the video on pulleys right here, and I'll show you what that looks like. The pulley video, I admit, is a little bit goofy. It's a cartoon. So enjoy the crazy cartoon about pulleys first before you start the lab. After you've answered the 6 questions about the video, make sure you read those questions before you watch the video so you can be watching for the answers. We'll go to part 2. We're going to use the CK12 simulation on pulleys. We're going to watch the intro and then go to the sim. I'll show you about the sim. Each graph in the sim has a gear in the upper right hand corner. You can click it twice to get info. And each slider has an eye in the upper right hand corner, and we'll talk about those when we get to the simulation. It looks something like this. Here are those little gears to get information about the graphs, and here are the little eyes to get information about the sliders. So here's the simulation from CK12 on pulleys. Let's watch the intro. It's about a minute or two. With simple pulley system shown, the worker is struggling to lift such a heavy box. Notice this is just a very simple pulley. When you add a single moving pulley, you get more mechanical advantage, and we'll talk about what that means in a moment. Let's understand the physics behind this. We've got the weight of the box. Weight, remember, is the force of gravity on mass. We've got the force of this person pulling. The moving pulley allows the force to be applied to the boxes to double in this case because we're pulling for a greater distance. Each length of rope he pulls, the boxes move up only half a length because it's not a direct relationship. It's going around the pulleys. Let's go to the sim and look a little bit more carefully. Let's look at all the information first. So this is info on the graphs. You can double click it and it says this is a plot of the weight of the boxes on the vertical axis versus the distance these boxes are lifted on the horizontal axis. A heavy box lifted a short distance will produce a graph that is narrow and tall, where a light box lifted a great distance will produce a graph that is wide and short. The area of the rectangle has the units of force times distance. We know these units to be the units of energy. The area, in fact, represents the work required to lift the boxes. This is the amount of energy the worker needs to expend to lift the boxes away from the earth. And ideally, since we're working in a simple machine system, the work on this graph for the work done on the box is going to be the same as the work done on the effort side by the worker. So this is the resistance side, and this is the effort side. So let's see what happens if we just kind of mess around with some of these sliders. So we can set our mechanical advantage to be more than 1 here. We can set it to be 2, and watch what happens to those ropes there when we change the mechanical advantage. I'll change it up to 3, and watch those ropes change again. So we have 1, 2, 3 ropes here, and you can change the weight. You can change the length of the rope pulled. Let's watch the relationship between the length of the rope pulled and the distance we raise the box when the mechanical advantage here is 3. So we'll pull 3 distance, 3 times the distance, 3 units of distance. And you can see that we only raised the box 1. So the mechanical advantage here makes you pull 3 times further then you raise the box. So the distance you pull the rope is 3 times longer than the distance you raise the box, but you only have to use 1/3 the force here. The force here is 0.33 units of force, and here the weight, the force pulling down of gravity, is 1. And you can see the work here is the same. This is 1 by 1, and this is 1/3 times 3. So the area in both of these graphs is the same. Okay, in the intro video, the first part of when we were looking at the sim, it says the worker does not get something for nothing. What does that mean? The worker needs to use less force, but what's the trade-off? If you use less force, you need more distance. We saw that in that he only raised the box 1 unit of length, but he had to pull 3 units of length on the rope. So the trade-off is less force, more distance. If we keep the weight the same, but change the mechanical advantage or distance, what happens to the graphs at the top? Well, we'll have to play around with that a little bit more and under some different conditions to see what happens to those graphs. Let's keep the weight the same and play with mechanical advantage, length of rope, and weight. Okay, let's see what happens if we change the weight a little bit. Oh, look, those graphs get bigger because more work needs to be done because you have more weight to lift. Let's change the mechanical advantage to 4. Did that change the total work done? Not really. It just made the graphs slightly different shapes. Let's go back to, I made this graph taller and skinnier. And this graph a little bit skinnier as well. All right, let's mess with the weight a little bit more. When we use more weight, we have to do more work. All right, if he hasn't pulled the rope as far, he hasn't lifted the box as much, he's only lifted the box about 1/3 a unit of distance here, you can see that the work goes way down. Let's max him out here and see if we can get him to pull the rope a whole bunch. And there you go. You've got more work done because he's pulled further. The distance has increased. When you increase the distance or the force needed, you're going to get more work. If we decrease the amount of weight, we decrease the amount of work. If we decrease the weight, we're essentially decreasing the force you need to overcome the force of gravity. All right, we've played around with these boxes. Let's go answer our question now. So when we played around with the mechanical advantage, the length of the rope pulled, and the weight, the amount of work changed. Those boxes got larger or smaller. If we increased the weight, they got larger because if you have something heavier to lift, you're going to have to do more work. If we increased the distance the rope was pulled, we got more work done because we raised the object a greater distance. And remember, there's 2 parts to the work formula. There's force and there's distance. So if you increase either of one of those, you're going to increase your work. Or if you decrease the distance or decrease the force, you're going to decrease the work. So number 9, we've talked about a little bit what happens to the pulley system when you increase the mechanical advantage. Let's go talk about a mechanical advantage a bit and answer this question a little bit more fully. Right now I have the mechanical advantage set to 1. And let's see how much force is required. We have a weight of 3, so 3 units of weight. are going to require 3 units of force. So that's a one-to-one relationship, and that's why the mechanical advantage is 1. It really, this pulley system isn't really going to give you any more oomph. It's not going to give you that trade-off for force and distance. It's just going to change the angle you're pulling the rope. And let's watch that here. Let's watch this guy try to lift this. He can do it because he's 3 units of weight. So he's got enough weight to pull against the box. But let's see if we make the box heavier than the worker, can't do it anymore. So we're going to have to give the worker some mechanical advantage. If we give him a mechanical advantage of 2, we make him pull twice as far, we increase the distance, we decrease the force here. See, the weight is 4 over here on the resistance side, but on the effort side, you only need 2 units of force. But you're going to need twice as much distance now. You have to pull it 2 units of distance to raise it 1 unit. That's why the mechanical advantage is 2. You need half as much force on this side as there is on this side, but you have to pull twice as far, so that there's that trade-off between there's a decrease in force for the worker, but there's an increase in distance. Let's look at mechanical advantage of 3. Notice what happened to the pulley system here. Now there's 1, 2, 3 lengths of rope, so he has to pull it 3 times as far. You can see it dropped a little bit in order to get it back up to 1 unit of distance. We had to pull 3 times as much. So the mechanical advantage of 3 means you only need 1/3 of the force here. 1.33 is 1/3 of 4 here, but you need to pull it 3 times as far. So the force goes down, the distance goes up. The work remains the same. You can see these bars are the same shape, or the same area. This is 3 times 1 1/3. This is 1 times 4. So you can play around with the mechanical advantage of the pulley system a little bit, slide that bar back and forth, and count the number of ropes and see what the relationship is. As we change the length of rope pulled, we need to know what happens to the graphs as you decrease the length of rope pulled. What's going to happen to the work done if you decrease the distance and everything else remains the same? See if you can make a prediction. So I've set it up so I've got, of course, work is the same on both sides. The area of the orange rectangle is the same as the area of the green rectangle, because both of these are force times distance, and force times distance equals work. Now, what's going to happen to the work, or the area of both these rectangles, if we decrease the distance or decrease the length of the rope pulled? Let's go all the way down to 2. What happened? The area of both rectangles are smaller, and those areas, of course, represent work. So less work is being done because there's less distance the rope was pulled. The object was moved a shorter distance, so less work was done. Okay, now we're on number 11. With mechanical advantage and distance pulled both set at 2 or above, let's change the weight of the boxes and see what happens to the graphs when we increase the weight. So I've got mechanical advantage and length of rope pulled both over 2. Let's see what happens when we double the weight. What happened to those rectangles? I'll let you think about it. So, number 12, the orange graph on the left, representing the pulley system, and the green graph on the right, representing the worker, both represent work is equal to force times distance. So it's the area of those graphs that's the work. Explain how work is being measured in both systems. So what's the force on the resistance side with the boxes hanging, and what's the distance being measured there. And then on the worker side, also explain what's the force being measured and what's the distance. Look at the area, length times width, covered in both orange and green graphs. What do you notice? Compare the area between those two graphs. Is it the same? Is it different? Mess around with the simulation. Do all the sliders. Try lots of different conditions and see what happens to those green and orange graphs, and keep comparing the area. So set the mechanical advantage to 4 for number 14 and the weight to 1 or more, and then try to raise the weight 1 unit of distance. What's the mathematical relationship or the ratio between the distance you raise the weight and the distance pulled by the worker? Why? Well, let's go find out. So I have mechanical advantage 4, weight 2. Let's see how much rope he has to pull, our worker has to pull, to get our weight 1 unit of distance. So not there yet. Not there yet. Not there yet. There we go. So length of rope pulled is 4 units of distance. Let's say it's like 4 meters. And the box only went up 1 meter. So that's 4 to 1. And notice the mechanical advantage is 4. So now you've got the answer to 14. Now let's do keeping the weight the same. Set the mechanical advantage to 2 and raise the weight 1 unit of distance. What's that mathematical relationship or ratio between the distance you raise the weight and the distance pulled? Why did it change from the problem above? Okay, so now we have the mechanical advantage of 2 and the length of the rope pulled as 0. Let's try to get this distance, let's try to get this weight 1 unit of distance up. So let's pull the weight 1 unit of distance, or rope 1 unit of distance. Still not 1 unit of distance up. Okay, well that's all it took this time. The mechanical advantage was 2, so you need half as much force required, but you need twice as much distance. This went up 1, we had to pull twice that distance of rope. But remember, the work's always going to be the same. Okay, now we get to have a little fun. Set the mechanical advantage to 1. So it's a 1-to-1 relationship between the distance you raise the object and the distance you pull. And there's a 1-to-1 relationship between the weight of the object and the force that you have to put out to overcome the force of gravity. And we're going to raise the weight to 4, the length of the rope pulled to 3. What happens? Let's go see. So mechanical advantage to 1, weight to 4. Well, look at this poor guy. He weighs 3 units of weight. These boxes weigh 4. Is he going to be able to pull these? He doesn't have really any mechanical advantage. It's a 1-to-1 relationship between the amount of force and the weight. Let's see if he can pull. Not going to happen. Can't do it. We're going to have to give him some mechanical advantage in order to be able to do that. Because he's not heavy enough to overcome the weight of the boxes, we've got to give a little mechanical advantage there, so he needs less force, only half as much here, because 2 is half of 4. Okay, so we talked about the mechanical advantage and how our poor worker needed some mechanical advantage in order to be able to pull it all, because his weight was 3 and the weight of the box was 4, so he couldn't pick up the box that was heavier than him unless he had some mechanical advantage. So now it's time to wrap it up use the words pulley, mechanical advantage, distance, force, work, weight, and graphs in 2 to 3 sentences to summarize what you've learned in this lab. Make sure you use all these words and you highlight them in your sentences because you get 1 point a word, so you want to use them correctly and you want to use them all. If you want to do the extra credit investigation, it's pretty easy. I can show you how to get started. Here's a screenshot. You want to make sure you check these boxes, and I'll show you how to do that when we get to the simulation. And then we can talk about some of these questions. This is a slightly more sophisticated pulley simulation, and it's just kind of fun to play around with. So give it a shot. It's an easy way to earn some extra points. So I've pulled up the Compass learning simulation, and I'm going to check these boxes. Work input, work output. These are kind of like our graphs in the last simulation. I want to have actual mechanical advantage and efficiency. Oh, and I want potential energy as well. So we have a single fixed pulley here, which is just a mechanical advantage of 1. So that's not great. Let's do a single movable pulley and see how that helps us. We have to apply some force here, and it will raise things for us. And you can see the actual mechanical advantage here of this pulley is 2. You can see that the work input and the work output is the same. And you can see that we've gained some potential energy. We've raised the weight this much, 0.1 meters. So we have some potential energy. If this falls, it's going to create some kinetic energy. Let's do this again with a double compound pulley. You can see there's 1, 2, 3, 4 strands here. You don't count the one you're pulling on. Let's up the load a little bit. Let's up the distance we're lifting a little bit. And let's keep friction at 0. Now let's see if we can. It's very slowly pulling on things. You can see that the work is increasing as the distance increases. The potential energy is increasing as the distance increases. And the mechanical advantage just stays fixed because the number of ropes is, of course, fixed. And we can see the efficiency here is 100%. If we turn up the friction a little bit, let's keep everything else the same, but put some friction in the system, because every system in real life has some friction. Let's see what we have to do. You can see the efficiency is a little bit less because some of our work is being converted to heat when we have friction in a system. And so the efficiency of our work is less than perfect now, and the actual mechanical advantage goes down a little bit. We're still gaining potential energy and we're still doing work, but you can see that the work here isn't the same. The work input, the amount of work we had to do to lift, is not the same as the work output, the work that we had to do to, or the work that was done to the weight. Because some of that work went into overcoming friction. It was still done, the work on both sides is still equal, but some of the work went into friction, overcoming friction, and that turned to heat, and that energy isn't lost, it's just now out in the, it's out of the system. It's has been transferred to heat energy, which isn't going to do any work for us in this particular system. So it's not lost, it's just not useful in this system. So you can play around more with this pulley system, answer the questions for extra credit, and earn a couple extra points. The last question for extra credit is write your own question for the simulation above. Think of a situation where students might be able to learn, have them set up certain parameters and then watch what happens. And you can write a question for the simulation and you can answer it, and that is worth up to 5 points. So if you kind of think outside the box a little bit, you can earn some good extra credit. Thanks so much. This is Miss R signing off on Lab 6.06 on pulleys.